So should I start?
Yes, of course.
Okay, so thank you very much for the invitation. Thank you, Jan and David, for organizing this conference and the other organizers. So my name is Gonzalo Manzano. I am going to talk about thermodynamics of computations, and in particular about how to deal with thermodynamics of computations when we have three difficult ingredients, which are unidirectional transitions, absolute irreversibility, and stochastic computation times. So I am a tenure track researcher at IFISC, which is the Institute for Cross-Disciplinary Physics and Complex Systems in Palma de Mallorca, Spain. And this work has been done in collaboration with David from Santa Fe, Buchacardes from University of Colorado and Santa Fe, and Edgar Roldan from ICTP. And everything is in this paper here, which has been recently published during this week. So as I was saying, our idea is to kind of provide or start to construct a theoretical framework for assessing thermodynamic cost in computations, in particular in Markovian computational machines. And our results reveal like different universal bounds and inequalities on quantities that lower bound the entropy production in the system. And we also obtain some fluctuation relations at the stopping times. So the article is very large. I am going to cover some part of it here, but I hope I will be like kind of clear about it. So let me just start by pointing that the link between thermodynamics and information processing comes back to the beginning of the 20th century. It's linked to names like Leo Szilard, who proposed the first information engine based on the ideas on Maxwell-Dimon thought experiment. And of course, Rolf Landauer with his well-known Landauer bound. He analyzed the heat that is produced in processes like bit eraser. And of course, Charles Bennett, who was also one of the pioneers of thermodynamics of computations. So all of these pioneering results usually are about simple operations, like for example, bit eraser, and in processes that are reversible or quasi-static processes, so that equilibrium thermodynamics can be used in order to analyze them. On the other hand, the real-world computers involve much more complicated tasks and occurs at fast times, so non-reversible processes, and in general, one needs non-equilibrium thermodynamics in order to deal with them. But during the last few decades, there has been this development of stochastic thermodynamics that provided us like a very general framework to deal with thermodynamics of quite general non-equilibrium processes. And this has promoted some in research, some new research in the thermodynamics of computation using stochastic thermodynamics and modern non-equilibrium thermodynamics that, for example, are discussed in this topical review here by David. Nevertheless, there is still no general theory for non-equilibrium thermodynamics of computations, and this is exactly where our work tries to contribute. So the general idea in which our work is based is to try to link two levels of description, one of which is the physical implementations of, for example, digital computers. Here I just put some examples in which we have like physical states, physical degrees of freedom, and we need some work in order to run these computers, and we have some dissipated heat, etc. On the other hand, we have the theoretical description that is coming from computational science, in which we have models of finite state machines, of tapes, and depending on the input symbols that some machine is fed, the machine changes, and so on and so forth. So it's a dynamics over symbolic or computational states. So the goal of our work is to try to link these two worlds and try to establish connection between the thermodynamic cost in, let's say, physical states or physical implementations of computers and the function that those computers are doing. Like, for example, what what computation, what specific computation they are doing, or what model, computational model they are performing. So what we have in mind with Markovian computational machines essentially are finite state machines, such as, for example, deterministic finite automata that are fed by input symbols. So here I just put one example. So this is a deterministic finite automaton that is recognizing bit strings that are divisible by 4. So here the dynamics starts in one of these 4 states, but this, in particular in this Q0 state. And as long as input symbols are fed into this machine, the state of the machine can change. For example, if we receive a 1, we go to Q1, then if we receive a 0, we go to Q2, and so on and so forth. So if we assign some probabilities for the initial input symbols, we can turn this into a Markov process, as I show here. So in this case, we have, again, these 4 states, and we can define some initial probability distribution, which in this case will be like a delta function over the state Q0, and then some transition probabilities that will depend in general on the probabilities that input symbols are entered. So this defines a time homogeneous discrete time Markov chain over a state space that is over this kind of computational states. So we can define trajectories over here, and we can have path probabilities. So we have kind of the framework that we would like to do to use stochastic thermodynamics. However, in order to make contact with the dissipation and what is really happening in the computer, we need to extend our description in time and state space. So the idea is that we now consider like a physical space. So we have other variable called y in a much bigger space than the space of the computational states. And we assume that this dynamics is continuous in time. In particular, we can assume that this is a time homogeneous continuous time Markov chain, which is comes described by some rates. And in particular, we will assume that this continuous dynamics over the physical space is periodic, so that if we assume that we have local detail balance at that level, we can define the trajectories over that space, extended space in time and state space, and, for example, calculate entropy production, as is given by this formula of Kullback-Leibler divergence between the path probability of forward and time reverse trajectories in this extended space. So the idea then is to then go from this extended space to back to the computational states, and in order we can do that just because of the properties of the Kullback-Leibler divergence. So we know that this entropy production will be lower bounded by this Kullback-Leibler divergence here, which we may call like the coarse-grained total entropy production in this process. However, here there is a subtle point, which is that since the process behind is driven, the Kullback-Leibler divergence that appears here, you have the original path probability distribution, which will be just the coarse grain of the original one in the extended state space. And there's this other one, which will be the coarse grain of the time reverse path probability in the extended state space. And this, in general, we will not know what is that if we don't know all the details on this process in the extended state space. So this is a problem. This is in contrast with what is usually the case when inferring entropy production and so on, for example, in biological systems. Because in that case, we go to non-equilibrium steady states. Non-equilibrium steady states, meaning that we have symmetric driving, then we have that this P tilde in this case will be just equal to the original P. So no problem will arise in that case. And this is why these techniques have been used so fruitfully in this kind of systems, for example, biological systems like molecular motors and so on, in non-equilibrium steady states. In our case, we could not directly apply these kind of techniques, but the idea that we have is that why not trying to instead of using the whole entropy production, the whole coarse grain entropy production, why not instead further decompose this entropy production into different contributions? And in order to do that, what we choose is to use this decomposition, which is called, which has to do with this quantity, which is called mismatch cost. We have been introduced in some papers before. The idea is that any cost function C, we can decompose on the mismatch cost and this residual cost, meaning that this mismatch cost will be the cost that we have if the initial state used for the process is not minimizing the total cost. In our case, the total cost will be the entropy production, and this mismatch cost will be the cost that we have to, the extra dissipation we have to pay if the initial state is not the state leading to the reversible path. So the idea in our case is to use this quantity mismatch cost in periodic processes. So the underlying process is periodic, and then so we call this distribution here mu the prior, which could be the distribution that minimizes entropy production in the process. In the case of periodic processes, this prior will be the same for every iteration of the periodic process, so that the idea is that we can go from the total entropy production in the extended state space to the coarse grain entropy production over computational states. In general, we don't know how to calculate, but then we can even lower bound that using this mismatch cost that will be just a sum of the mismatch cost produced in every iteration, that's in every cycle of the periodic process of over the computational state space. So the good thing of this is that this lower bound on EP only depends on the physics, only depend on the details of the physical implementation towards this prior distribution mu. And this prior distribution, so the mu prime is just the one period iterated initial distribution mu. So that and somehow we can condensate all the details about the physical implementation in just one distribution, and this is the only thing that we will need in order to lower bound the entropy production. If we don't know what this prior mu is, what one can do also is minimize over all the priors. So obtain the minimum of this quantity over every mu, and this quantity we refer as the minimal dissipation. In general, it's important to point here that these bounds are non-zero in general, and this is because if you look at here, so even if we start the process in the distribution mu, we will have that at the first iteration we will have so we will have just the same full variable divergence here and here. But then if we go to second, third, and more iterations, we don't have any more a zero cost, no? Because we will have here mu prime and here mu, so we will have a cost, and so on and so forth. So those are bounds that are greater than zero in general, and provide a lower bound on the entropy production in non-equilibrium processes. So the idea then is to develop a stochastic version of this quantity, this mismatch cost on periodic processes. And in order to do that, we use an auxiliary process, which we define in the following way. So we call it the path probability of this process, we call P bar. And it has an initial distribution that in general we assume to be just the final distribution of the original process. And then we choose some transition probabilities that are constructed from the original dynamics by just flipping the arrows and then multiplying by this factor that depends just on a reference distribution, arbitrary reference distributions R, and one time iterated reference distribution R prime. What we have in mind, of course, is to use for these reference distributions either the prior that I presented before for the mismatch cost, or the new that we'll refer to it as the one that leaves the minimum mismatch cost over different priors. So using this, we found that we can obtain a stochastic version of this intrinsic mismatch cost, so this mismatch cost for periodic processes, just using the log ratio of path probabilities from the forward and the auxiliary process that I have just introduced. And this has this form here. And immediately from this form, we can obtain a fluctuation theorem and a second law-like inequality. So as you can see here, this is convenient in the sense that even if we have unidirectional transitions, the auxiliary dynamics is flipping the arrows of the transition. So this quantity is well defined even if we have this unidirectional transitions. So a second point that we wanted to take into account is absolute irreversibility. So absolute irreversibility is a concept that has been introduced in this paper here in 2014. The main idea is that if you write what you put inside the integral fluctuation theorem, so e to the minus sigma, where sigma is the entropy production, or in our case is this mismatch cost, we found that this quantity can diverge for some unpaired trajectories. So for example, if I have a trajectory that in the forward process going from A to B is equal to 0, but in the auxiliary process from B to A is non-zero, then this quantity will diverge and we will not have the fluctuation theorem anymore. Instead, what we will have in that case is a modification of this fluctuation theorem and a modification of the second law, in which we have to include an extra term that in general accounts for the total probability of unpaired trajectories in the auxiliary dynamics. In general, it was first introduced for the entropy production, so time reverse dynamics, and in our case is regarding the auxiliary dynamics. So here you can see just an example. So imagine that we have a two-state systems with the states A and B. So the initial distribution is just a delta over B. And we ask, for example, to trajectories that go from A to B. So in this case, since the probability to start in A is 0, then even if we have some non-zero transition probability, the probability to A to B will be 0. Instead, if we look at the auxiliary process of this one, in which we start with the final state, the probability from B to A will be different from 0. So then this quantity will diverge. So this is just an example of this absolute irreversibility. Okay, the third element that we want to take into account is stochastic computation times. And in order to do that, this means stopping times. So in order to deal with that, what we use is a recently developed theory, which is called martingale theory for stochastic thermodynamics. So let me just briefly say what is a martingale process. So a martingale process is a stochastic process that were introduced by Paul Levy in 1934. And those are processes M that fulfill this property here. This property here, what it means is essentially that if I observe the evolution of a process M up to some time t, I can ask what is going to be the average of this process on a later time condition on the evolution that I have already seen. The answer is just the last observation that I did. Okay, so these are processes in which you have no drift on average. Okay, so your best guess for any further time, the mean of the process at any further time is just the last observation you did. So those processes are well known in mathematics of finance, where they are used to model markets in which the prices are equilibrated in the sense that that demand and supply is equilibrated, so that you cannot have any benefits just from buying and selling things on average. So that if this, for example, represents the price of a stock, if I observe how the price rises at some point t, and so then I can buy it, and I want to sell it afterwards, what the martingale property says is that I will not make money, not lose money from that, because the average will be just, the average price afterwards will be just the price that I pay at this point. So martingale processes verify many interesting properties, like for example, Doo's optional stopping theorem, that is a statement about the statistics of the process at general stochastic times, calligraphic tau. And they say that the average over trajectories of different lengths that are stochastic just go back to the to the statistics at time zero, for example. Moreover, similar properties can be derived for some martingales and super martingales, meaning that processes in which this we have instead of equality here an inequality in one direction only in the other. So the idea in our work is to identify a super martingale, which is this one here, is the exponential of minus this mismatch cost, and then we have an extra term which is called delta. This we introduced this in previous studies. It's called stochastic distinguishability, and in general, it's a measure of time of how is the time asymmetry in the distribution of the system with respect to a given process. In this case, is this auxiliary process. So, for example, we can think in some initial distribution rho zero, going forward in time with using the forward process and leading to some final distribution rho tau. And then if we start from here and go back using the auxiliary process, we in general have a different evolution for the density matrix, so for the probability distribution, which at any intermediate time will be different from the forward one. And this is essentially what this quantity tell us. So it's a way to quantify this. So using this process, we can verify that this is essentially a super martingale, meaning that the conditional average of this quantity over trajectories up to some previous time t is just the same process multiplied by this factor, which is always less or greater or equal than 1, so that this is always greater or equal than this one. Indeed, we can see that this becomes a martingale in the absence of absolute irreversibility, meaning with this alpha term here that we obtain is 0. And interestingly, this implies a fluctuation theorem for absolute irreversibility. Sorry. So that we can obtain just by extending Doomb's theorems for martingales to super martingales, and looks like this thing here. So essentially, we have an exponential of the mismatch cost and this extra term delta associated to this stochastic distinguishability. And instead of having 1 here, we have 1 minus this extra term, which is the total probability of the stop trajectories that are unpaired. So it's related again to absolute irreversibility, but in this case of the stop trajectories, the trajectories that are stopped in the different times during the process. So this allows us to obtain also some second law inequalities at the stopping times, like this one here, and moreover relations of that go for are valid for consecutive stopping times. So for example, so here for stopping times in the context of computations, we mean, for example, the time at which our computational machine, for example, stops because the computation is end. So, for example, we can, for example, look at these mismatch quantities between, for example, the acceptance of a first word by our machine and a next word, or many things like that. So, so this is interesting because it is even valid for stochastic, not only for stopping time, but also for starting time. So, this is this is related to the dissipation. It's a lower bound on the dissipation from some stochastic initial time to some stochastic final time, which is greater than this. So, sorry. So we can also obtain other different bounds that, like for example, this one here, that don't even rely on this extra term of absolute irreversibility. We can also obtain some upper bounds. We have also some extra fluctuation relations. We have also some other universal relations for the acceptance probabilities, but I have no time to talk about all this here. So I just decided to present like few main results. So let me just go to some examples. So one of the examples here is a deterministic finite automaton, which is fed by IID distributed symbols. So as the one I showed in the first slide. In this case, we assume that our reference density is just the invariant density pi of this Markov chain. So in that case, this mismatch cost reduced to the non-adiabatic entropy production. And what we obtain is that, so here you can see the value of this mismatch cost, or in this case, non-adiabatic entropy production, as a function of the probability of input symbol 0 for fixed times, which are these squares here, and for halting time, which are these field squares, field squares here. So one thing that we can see is that, first of all, is that our lower bound to the mismatch cost is saturated in this case. And another thing is that as long as this extra term delta is greater or equal than 0, we can have less dissipation at the stopping times than at fixed times. So this is also an interesting point. So another different example that we point in the paper is what happens if the input symbols are not IID. So what happens if they have some correlations? So, in this case, we analyze this other finite automaton, deterministic finite automaton, but in this case, we consider that the probability of the input symbol may depend on the previous symbol that has been processed. So in order to do that, what we have to do is to just duplicate the state space. So now our computational state as our computational space state is 6 states, not 3, as in like the previous cases. And then we build the transition probabilities depending on the probabilities that the next symbol is 0 when the previous symbol is 0, next symbol is 1 when the previous symbol is 1, and so on and so forth. Even in this case, we also obtain that bounds are quite tight. So for example, here you can see the mismatch cost as a function of the probability of having symbol 0 when the previous symbol was 1. For two different cases in which the other probability is different. And in both cases, you can see that our lower bounds are quite close to the mismatch cost. And here I didn't explain that, but we also have these upper bounds that you can see also here with dashed lines. So the red is for this case and the blue is for the other case. We also test, for example.
Sorry for interrupting. 5 minutes. You are already in question time. So.
Okay, thank you, Belver. So yeah, so let me just finish. Yeah, so in conclusion, so within our framework, we can bound dissipation engineering Markovian computational processes at arbitrary stopping times, and even between one stopping time and other stopping time. So the advantages of this setup is that we can apply it even if we have unidirectional transitions and absolute irreversibility. And a good point is also that our results are almost independent of the implementation details, so that essentially what we are calculating are the minimal dissipation that some computational models will require. And the details, so the remaining details are just inside this prior distribution that will minimize entropy production. So with this, we can, I can finish. So I thank you very much. I'm sorry for going into the questions time. And I will